Let's solve part B in this video. And in part B we want to know whether the function is differentiable, meaning that can we take the derivative at every point along the curve. Now before going on, why would we even ask this question? We saw in part A that the function is already continuous. So if it is continuous and we can draw it without any gaps in the graph, why would we bother? Why would we still have a problem? Let me show how this could be a problem. Because we can still have a function that's continuous but not differentiable at a certain point. Suppose this would be our graph, so it would look something like that. It's going a bit curvy, and then we have this sharp turn here, over there. That's f of x. Now we can see that the function is running smoothly. We have an actual y value for every x value. Now, what is differentiability? Differentiability is whether we have defined slopes, if we have defined rate of change at every point along the graph. Well, here we have a defined slope. We can take a tangent line to that point. Here as well. We can do that here too. But check this point over here. What is the slope there? The slope is increasing, and at exactly that point it suddenly starts decreasing. So what is it? Is it a positive slope or a negative slope? We don't know. This sharp turn says that we do not have a defined slope here, meaning that the function is not differentiable at this point. And that's an example where we have a continuous function but not differentiable. And that's the intuition that we're using in this question, because we saw in part A that the function is continuous, but now we have to see if it's going to be differentiable everywhere. And let's see, if we take the derivative of x squared plus 2x minus 3, well, the derivative with respect to x would be just 2x plus 2. Let's take the other derivative. Can we do it? I think we can. If we differentiate, it's going to be minus 2x minus 2. So the question is just like before. Let's check the critical points, the special points, to see whether the function is differentiable there as well. And when is a function differentiable? When the limit of the remember that formula, that general formula, when the limit of h approaching 0 from below, and if you don't recall this one, please watch my video that I linked in the playlist, the intuition of differentiability and continuity. I'm explaining there in more detail. So this thing has to hold that if we take the derivative when we increment x from the left side by just a bit, so 0.0001, and we increment it from the right side, we have to approach the same value. So minus f of x divided by h. And let's apply this concept into our question. Let me zoom out it slightly so we get some more space, and let's solve it. And let's do it for the point of x equals to 1. Let's see if we have differentiable function over there. So let's check the limit as h approaches 0 from the positive side of f of x plus h minus f of x divided by h at the point of x equal to 1. So what does that mean? That means that at x equals to 1 we'll substitute 1 into x. So we would have now the limit as h approaches 0 from the positive side of f of 1 plus h minus f of 1 divided by h. Okay, what is f of 1 plus h? First of all, we have to find out which function we're going to use, and this is going to be our new input in the function. So we are approaching h from above, meaning that the x value where we're incrementing is going to be slightly bigger than 1. When is x slightly bigger than 1? It's slightly bigger than 1 in this range, meaning we're going to apply this form of the function. So instead of having x, we are going to have a new input, which is 1 plus h. So we're going to have 1 plus h to the power 2 plus 2 times 1 plus h minus 3. Let's write that down. We have the limit as h approaches 0 from the positive side, and here we would have 1 plus h to the power 2 plus 2 times 1 plus h, and then minus 3. That's just for the first part. Minus, what is f of 1? Well, let's see, when can we substitute 1 into our function? Also in this range, and we put in 1 into our function, it would be 1 squared plus 2 times 1 minus 3, that's just 0. So we go down and we write minus 0 divided by h. Now, let's substitute 0 into h everywhere and see where the limit goes. We would have 1 plus 0 to the power of 2 plus 2 times 1 plus 0 minus 3 minus 0 divided by 0. And that's equal to 1 plus 2 times 1 minus 3. That's 0 over 0. And we can see that this is undefined. So we must use the L'Hopital for limits. So let's do it. We write the limit again and we'll take the derivatives of each side. We write the limit. H approaches 0 from the positive side. And remember, where did we stop with our limit? It was over here. We can rewrite this thing because that was just expanding the f of 1 plus h. So we will have 1 plus h to the power 2 plus 2 times 1 plus h minus 3. And then this was f of 1. So let's write minus f of 1 divided by h. And we are taking the derivative of each side. So the numerator over here and the denominator over here. We're differentiating with respect to h. Now, let's do it. So we have the limit, h approaching 0 from the positive side. And if we do it over here, what result do we have? We have the power rule, 2 times 1 plus h, but then it's an expression of h, so we're applying the chain rule where we're differentiating 1 plus h itself, plus 2 times 1 plus h derivative. 2 is a constant, and then we differentiate 1 plus h. Well, 1 derivative is 0, h derivative is 1, 0 plus 1 is just going to be 1. Minus 3 derivative with respect to h. That's a constant derivative, is just 0. F of 1 is just a value on the function. The derivative of a constant value is just 0. So we can write minus 0 divided by h derivative with respect to h. That's just 1. Okay, let's make it a bit more neat. We're almost done with this limit. So the limit h approaches 0 from the positive side. We have 2 times 1 plus h, 2 times 1 plus h. 1 plus h derivative with respect to h, well, that's just 1. Again, 1 derivative is 0, h derivative is 1. Plus 2, the zeros go away, divided by 1. So we got, if we substitute 0 into h, what's going to be the answer? Well, we will have 2 times 1 plus 0 times 1 doesn't change anything, plus 2 divided by 1. So we have 2 times 1 is 2, plus 2 is 4, divided by 1 is 4. That's the limit when h is from the right side. Now this was just half of the question. We have to do the same when h approaches 0 from the negative side, so from below. And let's do it. I know it's a bit time consuming, but that's one of the hardest topics, so you know, gotta pay the price for it. The limit of h approaching 0 from below of f of x plus h minus f of x divided by h, again at the point of x equals to 1. So that's going to be the limit as h approaches 0 from below. Now instead of x plus h, we will have 1 plus h minus f of 1 divided by h. So that's equal to, now the shape of the function should change because 0 is approaching from below, sorry, h is approaching 0 from below, meaning that the value where we're changing from x is going to be less than 1. And in our function, x is less than 1 over here, so that means we're going to apply this shape. So now we have minus 1 plus h squared minus 2 times 1 plus h, because remember 1 plus h is our new input, and then plus 3. So let's write that down. Let's write it over here. We have, just a second, we have minus 1 plus h to the power of 2 minus 2 times 1 plus h plus 3, then f of 1, we already calculated in the previous part, it's 0 divided by h. So let's substitute 0 into h and see what we get. We would have minus 1 plus 0 square minus 2 times 1 plus 0 plus 3 divided by 0, and that's equal to minus 1 minus 2 plus 3, that's 0 over 0, and again undefined. So the same pattern, if that's undefined we have to L'Hopital it. So let's L'Hopital it. The limit of h approaching 0 from below. Now where did we get? We got to this point, so let's write it, because we'll have to differentiate both sides, both parts, numerator and denominator. Plus 3. What was 0? That was f of 1. I'm just writing it to show that the derivative of it is gonna be 0 divided by h. So let's take the derivative of each side. We take it over here, we take it over here, and what do we have? The limit as h approaches 0 from below. Now power rule and chain rule, minus 2 times 1 plus h times 1 plus h derivative is just 1. I'm gonna slightly skip over steps because it's getting too long. And then minus 2 times 1 plus h derivative, that's 2 times 1, so minus 2, plus 3 derivative is just 0, f of 1 derivative is a constant derivative, is 0, h derivative is 1. Okay, let's substitute 0 into h and see the result. We have minus 2 times 1 plus 0 times 1 doesn't change anything, minus 2, 0 doesn't change anything, so we don't write them, over 1, minus 2 over 1 is minus 4. What do we see here? We see that the limit in this case is minus 4, but the limit in the previous case was plus 4. So we're not approaching the same limit, meaning that the function is not differentiable at the point of 1. So at this special point, the function is not differentiable. And let's suppose this is our example, because I think it's gonna be pretty accurate. If this would be the point of 1, let me change colors to make it more visible. If this would be the point of 1 at x equals to 1, we said that the function is continuous, okay, but then the slopes, you see, in one case it's a positive slope, and in the other case it would be a negative slope. So that's probably how it is in this case. From one side we have a slope that is positive 4, so the function is increasing, and suddenly it has a sharp decrease where the slope is negative 4. So the actual slope, the actual derivative is not defined at this point, and that's most likely the case. So the answer is that the function is not differentiable everywhere. And by the way, I saw in the answer key that it just says the function is not differentiable, but a more accurate way to say it is that f of x is not differentiable everywhere, because at many other points that we can check is gonna be differentiable. So f of x is not differentiable everywhere. And it's enough to prove it just with one point, because, well, if it's not differentiable at one point, by definition it means that it's already not differentiable everywhere. So f of x is not differentiable everywhere. We proved it with the example of x equals to 1. And that's it. We are done.